All right, good morning. Okay, let's start lecture. We'll continue in the review of vector concept. We'll finish this today, and then we'll get on the new concept now. Basically, it's plane equations in 3D space. Okay. So, how's the voice sounds like in the back of the classroom? Is it okay? Okay, good. All right. Let's continue. So in the previous lecture, we reviewed the vector concept and then the basic concept for vector. And I want you to remember firmly that, which is basically given a vector, it has two information. One is magnitude. Oh. Good. Alright, so given a vector, basically, you should remember vector consists of two things. One is magnitude, the other is direction. Okay, so this one here is magnitude or length, and this one here, and this one is direction. Running out of battery. Okay, so that's the important concept for vectors here, okay? Yeah. And we also reviewed the dot product. Given two vectors A and B, then the dot product A dot B is equal to this formula here. So dot product gives us basically a scalar quantity here. Okay, yeah. And we use dot product to have the basic application, which is the projection of one vector to the other direction. So if I have a vector A at here and the vector B at here, and if I wanted to know what is the projection of this A vector in the B direction, so I use B hat at here. And in the previous lecture we derived, essentially we need a new vector, which is this one here. So this is the new vector we're looking for, the projection of A in the B direction, right? So any vector has two components. One is the length, the other is the direction. So if you look at this new vector, it's no difference. So the new vector has a length, has a direction. And direction is very straightforward. Direction is this direction given by the B vector, which is B hat. The length, which is basically the length of this portion right here, and that happened to be A dot B hat. A dot B hat. So this is something I emphasized in the previous lecture. What is the physical meaning of a vector dot another univector, right? You see here, this is basically a vector dot a univector, right? That's mathematically what it looks like. Physically, what it basically means it's the length of the projection here, right? So you see here, this is basically means it's the length of projection. So in other words, whenever people ask you, can you give me the length, the projection of a certain something into certain direction? What do? Mathematically, you can just use this vector representing that A, and then dot the new direction, not univector of the direction, right? and you get the projection links. Okay, yeah. So that's dot product. All right. There are a couple of examples in my lecture notes. You can take a look at it. Okay, so I think all I need to do is just review the the concept here. So let's take a look at the cross product. Okay, the concept cross product. Cross product, very similar. So what you do is you're given two new vectors here. Let's say A and a B. Okay. So this time you draw this A and a B at here. Let's see, we draw A at here and a B at here. I'm going to draw them, okay, into a plane. So geometrically, as we learned in high school, given two vectors, they form a unique plane, right? You know, you cannot have another plane passing through these two vectors in here. So what we do at here now is in terms of cross product. And the definition of the cross product is, so A equal to A cross B equal to A times B times sine theta. Okay, so this is theta here, and then times n hat. Okay, so that's cross product definition. Low battery. So if you look at the cross product definition at here, it's still the okay. So if you look at the cross product definition, compare the difference between dot product. So look at this one here. So this is what? This is the length quantity, right? And what's this? This is the direction quantity. Okay. Yeah. So the difference basically is between the dot product, cross product. Dot product is a scalar, and cross product is a vector, right? It's a vector. So then, which direction does it pointing to then? The definition of cross product is it pointing to this way. Basically, this is your n hat direction. Okay, this is n hat direction, and this length at here, okay, is this portion. Okay, so this is length A, B, sine theta. Okay. That's the definition of cross product at here. And it yields a vector which is perpendicular to the plane formed by A and B. Okay, so we actually use this quite a bit when we deal with the planes in 3D space. So I'm going to just write it here. So n hat is perpendicular to the plane formed by A and B. That's cross product. And as you learned in the previous lectures or classes, dot product cross follows this so-called right-hand rule, right? So you curve your hand from A to B, and the thumb direction gives us the n hat direction. Okay? That's basically what a cross product is. And if you use B cross A, then basically you're having a completely different direction of n hat, right? Yeah. And the other thing you can also imagine at here. So if this is the length of the cross product, if I have A and B, the length of A and B fixed, if I change this angle between A and B, can you imagine what happened to the cross product results at here, the length of the cross product? What happened when theta equal to 0? When theta equals 0, what's the length at here? 0, right? Because sine theta is 0. And it also makes sense because when theta equals 0, B and A basically they become what we call coincide with each other, or sometimes we also call it parallel to each other, because vectors are free, right? You can always separate two vectors apart from each other. So two parallel vector, right? Two parallel vector, they actually don't form, or two coincide vector, they actually don't form a plane basically. I'm going to use this microphone here. Okay. Apparently there's no brand new battery over here. It's all used ones. So if you keep going, expanding this theta angle right here, right? If you keep expanding the theta angle right here, and you can imagine that basically, because of sine theta, the curve goes like this. Okay, so this is 0, this is pi, and this is pi over 2. So you can imagine when it goes from 0 to pi over 2, the magnitude reach maximum. As from going from pi over 2 to pi, and the magnitude of the cross product goes from maximum back to 0, right? Back to 0. So that's the nature of this cross product here. Okay. All right. Now, in terms of the application cross product, there are a lot of applications in your first year. You actually learned magnetic field and the current. Basically, when you curve up the finger with the pointing direction of the thumb, the direction as the direction of the current, then that's the relationship between your magnetic field and the current, right? Yeah. Now, in terms of calculation of the cross product, the actual calculation cross product, there's a different formula here. So, given, let's say I'll use 3D vector for example. Okay. So let's see, my A vector is A1, A2, A3, and B vector is B1, B2, B3. Okay. So you have specifically the vector given in here, and you're required to calculate what is A cross B. Okay. So in this case, using this formula wouldn't be too easy, because yeah, you can calculate the magnitude A, magnitude P easily, but we don't know the theta, right? And the theta is not given directly. You can calculate theta, but it's not given directly. So here is an alternative formula you can use for cross product. Here's the formula basically. As a matter of fact, I will introduce 3 notations at here. Okay. So here's alternative calculation of the cross product. So what exactly does these symbols mean in here? So first row, okay, first row here are 3 unit vectors: I hat, j hat, k hat. Remember, we use a hat symbol on the top of a letter to indicate unit vectors, right? And also remember that when I draw vectors, I always draw a 3D coordinate system first. So when we draw the coordinate system, we have x, y, z coordinates, axis, right? So for each one of the axes, okay, it's a vector, and we use I hat, j hat, k hat to indicate the unit vector pointing in that direction. Okay, so that's the symbol in this class: I hat, j hat, and the k hat. Okay, indication of the unit vector in that x, y, z axis direction. Okay, and that's basically what the first row is: I hat, j hat, k hat. And the second row is the A vector here, and the third row is the B vector here. So that's this matrix, 3 by 3 matrix, and then sandwiched by the 2 vertical lines here. And essentially, basically, this means is a determinant. Okay, looking for the determinant of the 3 by 3 matrix. Okay. We learned this one in your 179. All you need to do is you basically expand this this 3 by 3 matrix row by row. Okay, so first you use, essentially, if you cross this out, right, you calculate the determinant of this one here. Okay, then you get A2 times B3 minus A3 times B2. and then times I hat, right? Times I hat. Okay, and then you keep going for the second. If I expand along the first row here, then basically, and this time you cross out this row and this column, and then calculate the determinant of this one. But in this case here, you have a -1 to the power of 2 plus 1, which become -1. So it should be a negative instead of plus. So negative, and then A1 times B3 minus A3 times B1, and then times J hat. So that's your second term. And then third term will be to cross this row and this column, and then calculate this determinant, which is A1 B2 minus A2 B1 times K hat. Okay. So that's the calculation. So you can see you already have A1, A2, A3, B1, B2, B3. All you need to just substitute here, and you keep the I hat, J hat, K hat. You get a vector essentially. That's what the cross product does. The cross product gives you a vector, and this vector here is a 3D vector naturally. So that's how you can calculate the cross product here. Okay, yeah. Okay, so that's basically the cross product. Okay. In the assignments, okay, sometimes I have, or in lecture notes, sometimes I give you some sample MATLAB or Maple code for you actually able to automate the calculation or to help you with the calculation. MATLAB and Maple are all available on the university campus computers. I think MATLAB is also free to students now, so I encourage all of you to actually to install it. You know, even though I don't teach these things in my course, but if I have any sample code, try it out, right? It'll help you in your future courses. Yeah. So, for example, in MATLAB, you can use this command called the dot, and then put AB over here. You can calculate dot product. You can use another command just basically called a cross. And you can use this command to calculate the cross product. Right, cross product. Now, here's a tricky one. I want you to study yourself at here, okay? How do I get the angle between A and B? Okay. So, here's one method I typically use, which works well for all different kind of situations. I want you to study yourself. If you want, you can try it out yourself. I use a function method called ATAN2 to calculate this angle. And within this function, we use a command called a norm. So basically, norm calculates the length, and then norm here cross. So that's the first term. This is a cross product AB. Calculate the norm, calculate the length of the cross product AB. And then the second one is a dot AB. Okay. So think about it, how this works. The return of this one gives you basically the angle between A and B and here. Okay. Yeah. Okay. So. Any questions? So I didn't do any exercise for the review. It's just purely concept at here. Okay. You can take a look at the first lecture notes. There are some examples if you wanted to practice a little bit. Okay, so if there's no question, now let's continue at here. So the rest of the material, I wouldn't call it a review anymore. They are very much related to our new concept now. Okay. So, but the first concept, what I wanted to do is to derive plane equation 3D, but I need to introduce two formulas first. One is the area, okay, of a parallelogram. Okay, so let's look at what's the formula for calculating the area of a parallelogram? And then we'll look at the volume of a tetrahedron. Okay? So what is a parallelogram? So here is the shape. So let's say given a vector A and B. Okay. And I'm going to put the A and the B, okay, put them together, okay, tail to tail. And then I will use these two vectors, okay, these two vectors to form a parallelogram. So here is the parallelogram we're forming up with these two vectors here. So that's the parallelogram. Alright, so then the question here is, what will be the area of the parallelogram here? Okay? Now, you learned this in high school, how to calculate the area of a parallelogram here. But I wanted to calculate this area of the parallelogram using the concept of vectors, okay, that we just learned at here. Okay. So let's say the angle between A and B is separated by theta angle here. Okay, so I'm looking for the area. But I'll start the basic concept, okay, that you learned from high school. Okay. So here's the height. Okay. If you drop from the top point to the bottom here, here's height A. So as we learned in high school, you calculate the parallelogram basically is the bottom length and then times height. Okay, that's the basic formula for calculating the area of parallelogram. If it's a triangle, then you put a 1/2, right? Okay. So now let's translate these things, okay, into the given conditions. What is the bottom length? Bottom length is the length of the vector A at here. So now bottom length, I'll replace that with absolute value, okay, the norm of the vector A. Height, I'll keep it a height for now. Right? So that's the H symbol. Okay. So far so good? Yeah. So it's a mixture of two things, right? So we don't want a mixture of two things. What we really want is consistent symbols. Okay. So let's take a look at the H here, right? So if I want to translate the H into the given conditions here, H is what? This is the right triangle here. And here's the theta. Here's the hypotenuse here. And the length of hypotenuse is B at here, right? So in other words, the H can be expressed using the length of the B and the theta angle. And that's B times sine theta. It's B times sine theta. Okay, I guess it's probably still not very simple enough. So I want to further simplify this a little bit. But if you're here now, if you look at what we have just reviewed here, what does this remind you actually?
Cross product.
Exactly. But it's not a cross product though, right? It's the what? The length of the cross product. So it's the cross product, but it's the length. So it's the A cross B, the length. Okay. That's the area of the parallelogram. Good? Alright, so now I'm going to extend this a little bit further now, okay? So now we know the area now, so next time it basically, what's the area of the parallelogram? You don't need to use the bottom length times the height anymore. You can just use the vector concept to obtain the area. Okay, so let's look at the next one here, okay? Let's look at the volume. The volume of a parallelepiped. It's a relatively relatively long words at here. the volume of a parallelepiped. So let's take a look at what exactly does this parallelepiped actually means in it here. Okay. So here's what it means. So I'm going to move up a little bit. Everyone following here? It's okay? Yeah. Okay. So same thing. I'm given, say that I'm given 3 vectors, A, B, and C. Okay. So I'm given 3 vectors, A, B, C. So here are the relative relationship between the 3 vectors here. Okay. So here's B, and this is A. Okay. The 3 vectors are placed in 3D space, okay, and they are not in the same plane. And they're not in the same plane. And I'm going to draw the C vectors here, which is, I use the red color here. So this is a C at here. Okay, so that's A, B, C vectors. Okay, labeled it on the top. So if you can visualize this, then what happens is B and C, let's say, are sitting on top of, sitting inside this table here. And the A vector is protruding out of this plane right here. Okay, so that's this relationship. And then we are going to form the so-called parallelepiped. Basically, you create a parallelogram at the bottom first, okay, and you basically create a parallelogram on each side, okay, using these vectors here. Okay, so that's a parallelepiped. Okay, that's a parallelepiped here. And we're looking for the volume of this thing, given the 3 vectors A, B, C. Okay, good. Okay, so let's see how we can get on with this kind of question in here. You can always essentially draw some assistant lines to help you with the calculation, right? But before we draw anything here, let's write down the most fundamental volume formula, okay, for calculating a parallelepiped. So if I wanted to calculate the volume, then I need to know the base area. The base area. So in this case here, you have 6 sides, right, of this parallelepiped. You can choose any side as your base area. So I'll choose this bottom here as my base area. Okay. And then base area times height. Now, that's your typical formula for calculating a parallelepiped. So what is the height then? The height basically, because the 2 surfaces are parallel to each other, the top and the bottom, so you can simply drop vertical lines, okay, from the top plane to the bottom plane at here. Okay. So the vertical line here representing will be the length h, right? H at here. So that will be the h, and then the bottom here will be the base area. So good? Yeah. So now when you look at this formula here, right? So let me continue the formula here. What's the base area? The base essentially is a what? It's a parallelepiped, right? A parallelogram. What we just did is area of a parallelogram. So now if I ask you what is the area of this base area here, what's the area of the base, then how would you write it? C cross B and magnitude, right? Magnitude, okay? Or B cross C, doesn't matter, okay? Yeah. As a matter of fact, I'll use B cross C here. Because the magnitude, so that doesn't matter, but of course, if you don't have the magnitude, it matters. Okay? Yeah. Good. That's what we just did. That's the base area. So now let's take a look at the height, right? The height at here. So now this actually, I need you to think back a little bit, 3 steps back. Actually, probably 3 steps back. The beginning of the review of the dot product now. Okay. If I want to know the h at here, right? H at here, and I want you to use the physical meaning of the dot product, which is what? If you think back at here, at the beginning. So how do I get a length? You use a vector dot certain direction, unit direction, right? Unit vector. Then you get the length, right? You get the length. So let's come back here. Here is the vector, isn't it, right? Here is the length. So basically, where is the length from? The length is actually from what? From the projection of the A to what direction? H is not a direction? To what direction?
Perpendicular to the plane.
Perpendicular to the plane, right? Direction perpendicular to the plane. So now the question is, what is the direction, the perpendicular to the plane formed by B and C, right? So here is the plane here. So I need a direction that is perpendicular to the plane formed by B and C. So let me call it, let's call it n hat at here, right? So n hat is perpendicular to B and C. If I can find n hat, then all I need to do is I use A dot n hat. That'll give me the h, right? That'll give me the h here. So now you think back 1 step back here now. How do I get n hat? N hat is perpendicular to B and C, and that's naturally what? The results of the cross product, right? The cross product. So we learned that B cross C, right, is perpendicular to the plane. B cross C that is perpendicular to the plane formed by A, like here, right? Okay, good. However, B cross C is not a unit vector. So what do we do then? Absolutely, right? Excellent. Then you divide it by its magnitude. That gives you the n hat, right? See, that's kind of logical thinking at here, right? So you're making use of all the pieces, little puzzles here to get this thing. So now all I need to do is now the height. So h, right? I can see the h equal to basically A dot n hat, right? A dot n hat. Is that clear? So I'll move down a little bit here because I don't have any space at here. So I'm going to move down this, just writing down over here to give me a little bit of space. Okay. And the height is A dot n hat, and I'll write out the whole formula. Good. So far so good, right? So you're basically making use of the very fundamental concept to form up the information set here. Okay. And once you have this, you actually will be able to see, well, look that you can actually do some simplifications, right? Because this is a scalar quantity, this is a scalar quantity. You can cancel these two. Once you cancel these two, all you're left with is A dot B cross C. Now this is the results, right? So you're given the 3 vectors A, B, C, and then you're looking for the volume form of the parallel piping formed by A, B, C. And then the results that here basically tells you is, what do you need to do? You just need to use A dot the results of the cross product B and C, which of course, so you calculate this first, and then you calculate dot product. You end up with a scalar quantity, right? And which makes sense. That's your volume quantity. Okay. Good. So that is the volume in here. Okay. Now this thing here has a name called triple scalar product. So this thing here is actually called triple scalar product. Now remember, just before we move on from here, remember the way we derived this formula is we picked the base area, which is the area formed by B and C, right? Now, because there are how many sides? There are 6 sides of this parallelepiped. So technically, you can pick any sides as this base area. But if you do that, right, if you pick a different base area, then instead of BC as the base area, and for example, we pick AC as the base area, then the formula will slightly change. So essentially, you get slightly different formula. For example, you get C dot A cross B, and you get maybe B dot A cross C, okay, which all give you the same results essentially. So they're all called triple scalar product. And what's even more interesting, and which I won't prove it here, is so you can prove that, okay, this A dot B cross C, okay, so I should use capital, sorry, use a capital here. For this particular triple scalar product, A dot B cross C, you can prove that this is equal to determinant A, B, C. So what does this mean? Basically, you calculate the determinant. Essentially, you put the first row as A1, A2, A3, second row B1, B2, B3, C1, C2, C3. So that's what this determinant ABC means. And if you put this first row A, second row as B, third row as a C, and you calculate determinant, that's exactly the same results as this one here. Okay? Yeah. So clear? So that's the 2 concepts. And I wanted to cover first before we move on to the plane equations here. So now let me ask a very simple question now. Okay, let's see how fast you can answer the question here. Yeah. So here's a question. So what if A, B, and C, okay, and they are all in the same plane? If A, B, C are in the same plane, what's the volume?
0.
0. Good. Okay, because I'm going to use these results next. Okay. Yeah. All right. Any questions so far? It's all good. All right. Okay. So we're pretty smooth. So now let's take a look at the next topic now. What's the equation of a plane in 3D space? Well, so far, previously in your calculus course, mostly you have dealt with our 2D planar case. A line, right, a curve, which are all in the XY plane. But in this course, the things extend basically to n-dimensional, but in most cases I use 3D for illustration at here. Yeah. So let's form a plane first. Yeah. So I'm going to place the plane in 3D, right? Now, to make it a little bit simpler, so let's give some informations. Suppose I have 3 points given. So I have 3 points given in 3D space. So let's say the first point is P1, second point P2, and third point is P3. All right, so that's the 3 points. As we learned, as long as the 3 points are not at the same location, so then you will be able to form essentially a plane, right, given the 3 points. So let's say this is P1, P2, and P3. Okay. So as long as the 3 points, they don't coincide at the same location, then you will be able to form a plane which passes through all the 3 points. It actually will form a unique plane, right? It won't be multiple solutions or infinite solutions. So it will be one single plane passing through this P1, P2, P3. Okay. So let's say I'm looking for is this the equation for this particular plane at here. Okay. Now, when you describe something, right? When you describe a quantity or a curve, so you describe that with a general equation, right? In xy plane, you always have an equation which has x, y as a variable. Okay. So it's very similar. So if I want to describe this plane, so I might want to basically do is I need to describe it using x, y, z variables. So let's say I'll pick an arbitrary point P, which is on the plane at here. So x, y, z. Okay, so that's an arbitrary P point representing a point on the plane. Okay. So now I'll make use of the vector concept that we just learned in here to derive this plane equation. So I will form a few vectors using the available points. Okay. So we just formed 3 vectors given based on the points P1, P2, P3 and the general point P. Okay, 3 vectors we just point in here. This is P1, P2. This is P1, P3. And this is P1, P, right? That's how you form the vectors using the points. Good. So now it's time for us to make use of what we have just learned in the previous example. You got 3 vectors that are here. If I make analogy of the 3 vectors to the 3 vectors which I just did in the previous example, A, B, C. So it doesn't matter which one you use. Let's say this is your A here, and this is your B here, this is your C at here, right? So it happened that the 3 vectors now, they're all what? They're all in the same plane. So then, if I can visualize a parallelepiped formed by the 3 vectors, that the volume is going to be 0. So which means the determinant formed by P1, P, that's my A vector, right? And the P1, P2, that's the B vector. And then P1, P3, that's the C vector. Right, that's basically the volume of the parallelepiped that we have just calculated. Okay? And it's alternatively writing as A, or this vector dot B cross C same meaning, right? Same meaning. And this is 0 because that's the volume. Okay, so this is 0 here. Okay. Good. Now you look at this, okay, you actually almost have an equation now. Because why? If you look at this, especially if you look at the second one here, right, the second equation here. What's given? P1, P2, P3 are given, which means you'll have P1, P2, right? You're also all going to have P1, P3, okay? And then you can calculate the cross products. Basically, you'll end up with some kind of vector from here. And then P1 is given. So when you substitute P into here, the P1P will give you a vector containing the general x, y, z variables. And then you use that dot, a known vector here. Can you visualize what happened at the end? You basically end up with just one single expression, right, which equal to 0. And that expression contains this x, y, z. That make sense? Yeah. So that basically gives you this equation already here, right? Yeah. But I really wanted to make it a little bit simpler, a little bit more meaningful here, okay? So here's what I want to do. And let's take a look at this first. Take a look at this P1, P2 cross P1, P3 first. Okay? P1, P2 cross P1, P1, P3. Okay. Okay. So P1, P2 cross P1, P3. If you look at this one here, what exactly this? This is cross product. Basically, what does that give you? It gives you essentially, as a definition cross product, it gives you a vector which is a perpendicular to the plane, right? Which is a perpendicular plane here. So I'm going to call this is n at here. Okay, call this is n here. Good. Now, if this is n at here, then I'll simplify my writing at here now as P1P dot n equal to 0. Okay, dot n equal to 0. So remember, this is what I derived from here, okay? So this is what I derived here. And this is derived from the given condition. So you see the logic flow here, okay? So given condition yields this. From here, you yield another results like here, okay? As this. So to put it in the words, right? To put it in a simple words at here. So now I can state that basically we can state. Okay, so we can state that this P, okay, x, y, z, okay, this P, x, y, z, which is the general point that we picked, right, from the 3D space. So this P is in the plane. Okay, so I can state that this point is in the plane if and only if this P1P dot n hat equal to 0. Okay. Dot n hat equal to 0. That's the condition. How do I have numerous points in 3D space, right? Numerous points in 3D space. Then how do I know that that particular point is on the plane, on this particular plane then, right? So here's the mathematical verification. If and only if P1P dot the n vector equal to 0, then it guarantees that P point is on that plane. That makes sense? Right? And P1P, or when you have a vector dot another vector equal to 0, geometrically means what? The two vector must be? Come again? Orthogonal, exactly, right? Yeah, it must be orthogonal, so, or perpendicular, let's put it. So basically means this P1P must be perpendicular to P, right? To the n here, which of course makes sense. Look at that, because n vector is perpendicular to this plane. It must be perpendicular to any vectors in the plane, okay? Yeah. So it's important to understand this actually here, because the next step here is then, because see where the n is from, right? N coming from the cross product. coming to cross product. So I'm gonna assuming let this n at here. Okay, I'm gonna let this n. Remember, the n is the perpendicular vector to the plane, and I'm gonna let it equal to a known vector or vector using symbols. Okay. So I'm gonna let n equal to a I hat b j hat plus c k hat. Okay. So this is my n vector. Always remember, this n vector is a what type of vector? It's not arbitrary vector. It's a vector what? Perpendicular to the plane. Okay? So remember, n is perpendicular to the plane. Okay? So that's not arbitrary one. But then again, if this n is perpendicular to the plane, so imagine you already have a plane now. How many possible n vector could you have? Infinite. Okay, they're infinite. So any vector times a scale, different scale, right? You get a completely different vector, even though they all point to the same direction. Okay? Yeah. If you flip the direction 180 degrees, then you get a different vector too. Okay? Yeah. So here's my n vector here. Here's p1 p dot, the n vector to 0. So now I'm going to apply this a simple dot product concept here. So let's first calculate what's p1p. So p1p equal to x minus x1 plus y minus y1 plus k plus z minus z1. Okay. That's p1p. And x1, y1, z1 are the coordinates for the point P, which is known, okay, which is known here. X, Y, Z are the general variables. So now I'm going to use the dot product, use the P1P dot, the n in here. And this dot product basically means you multiply all the I components, B components, and K component, and then you add them together, right? So that gives you A times X minus X1 plus B times Y minus Y1 plus C times Z minus Z1. Okay, that's the dot product, and this needs to be 0, right? This needs to be 0. So this expression in here, okay, is the plane equation in 3D space. In 3D space. So I want you to take a look at this equation, right? It doesn't take you more than 1 minute to completely write it down, memorize forever. But if you look at this equation, right, if I just write down the equation here, what I want you to actually to remember or understand is, what does A, B, C represent? What does X1, Y1, Z1 represent? That's actually the key point for this equation here. So, for example, right, we have just covered, where does this A, B, C come from? Coming from this vector n. And the vector n is a vector perpendicular to the plane you're looking for. And what about the x1, y1, z1? It comes from the point P1. Okay? Which means basically P1 is a point on the plane, right? It's a point on the plane. So now let's think backwards now, right? Think backwards. If the question is to derive the plane equation based on a certain given condition, okay? Certain given condition. I don't know what kind of given condition, but let's say you get given certain condition, right? Yeah. Then, in order to derive the plane equation, first step, you write this down, right? You write this down. And the second step, what do you strive to find the unknown? You need to find a point on the plane. And you need to find what? a vector ABC that is perpendicular to the plane. If you can find these two information, and all you need to do is just substitute in this equation, and you get your plane equation. Does that make sense? Right. So here is basically the two information which I have just mentioned. For a plane equation, so what you need is, you need a point on the plane. When you're deriving for a plane, how many points do you have? How many available points do you have on the plane? Literally, you have infinite, right? Infinite. As long as you can find one, or you can use just one point on the plane, that's enough, right? And second of all, what you also need is, you need a vector that is perpendicular to the plane. Okay. So I don't know how you can derive that, but there are many different ways you'll see that you can derive for a vector that is perpendicular to the plane. But you need that vector to be the coefficient ABC at here. Okay. So if you can find these two information, plug it over here, then you get your plane equation essentially. Is that simple? Okay. Now, the plane equation can have a different manifest here. So sometimes, okay, in some textbook or in my writing at here, so I multiply the A into the bracket, B into the bracket, C into the bracket, and then group things together. So let's take a look at what happens in here if I do that. Okay, I'll multiply A, B, C into the brackets. Then we get AX, okay, and then minus AX1, B1 minus B1, CZ minus CZ1 equal to 0. Okay. I'll group similar terms. So that gives AX plus BY plus CZ. So grouping this. Okay. And then the rest of the term, they are literally constants, right? If you have the points picked, you have the vector, perpendicular vector chosen, then these three terms, they should be constant, right? It should be a constant term. So okay, so that's a constant term. And now I'm going to move this term, all the constant term, to the right side, okay, of this equation. Then, so I'm going to save myself a little bit here. So then you get this expression here, right? This expression. So now the original plane equation, okay, seems to be simplified a little bit to this. And all of the right side, okay, is literally just a constant term. So you probably can call it a D at here, right? Call it a D. So that sometimes what you see for a plane equation, it's just simply in this format now. Okay, it's just simply in this format. So now you see you have two different plane equation formats at here. Okay, one is this one, and one is this. Now, when you solving a question, and my suggestion is always actually start with this one, because you need to find a point on the plane, you need to find a vector perpendicular to the plane, and then you plug it over here, you get your plane equation. In exam, you can simplify. If you don't simplify, I won't treat you wrong. Okay, so that's basically the bottom line. Okay. Okay. So before we move on, let me ask you a very simple question. Okay, a very simple question in here. So you can imagine, let's say I have x, y here, x, y, z coordinates. Okay, so you can imagine basically you can draw any kind of planes, right, in the 3D space. okay, in the 3D space. However, there is one type of plane, right? There's one plane. That plane, let's say probably it's one kind of plane. That plane will pass through the origin. Okay, that plane will pass through the origin. Not all planes pass through the origin, right? Yeah, but there's one plane pass through, and then they're infinite. So you can imagine if you tilt it here and there, right? And there will be infinite number of planes passing through the origin. Okay, yeah. But if a plane passed through the origin, okay, so if a plane passes through origin, what's this capital D equal to? 0. Excellent, right? How did you get a 0? You plug the x, y, z with the point, right? Which is origin, which is 0, 0, 0. So that D will be 0. Okay? Yeah. That actually gives you a sense what this D actually means sometimes. Okay? Yeah. Especially later, we'll have some more exercise to compare some relationship between two planes. Okay. So the coefficients that are here, it does make a difference. Okay. Good. So let's take a look at a few examples. Okay, and then we can carry on. Yeah. I'll give you a plane, okay, which is written down at here, and also a vector V. So given a plane, given a vector, the question here is, what's the relationship between this vector and this plane? Relationship essentially means you can always draw just to illustrate the situation here. So here's a plane, right? And here's a vector V. Before we derive for this particular example, maybe can ask yourself here, what would be the possible relationship between a vector and a plane? What would be possible relationship? Intersect. Yeah. Intersect basically means the vector V and the plane at here, they somehow will form a certain angles, right? Yeah. Now always remember, a vector is a free vector. So you can literally move the vector all the way around in 3D space, right? In 3D space. Okay? Yeah. What could be other relationship between? So if the V form vector, what would be a special relationship between V and the plane?
It could coincide.
It can coincide. Basically means you can put the V like this, right? But if as I said, V is a free vector, so I can move the V over here, isn't it, right? So now this V literally is actually parallel. Okay, so this is another relationship. So I can see if a parallel that cannot include the special case that's inside the plane at here. Okay, so that's another connection. So that's a parallel. What's the most special relationship? Sorry? Normal, yeah, exactly. So the V, right, is perpendicular to the plane. Yeah. Could be the other direction, right? But that's perpendicular. Good. And I think that's all we could have, right, for a relation between a V and a vector. Okay. Later, actually, next lecture we're going to learn lines. You actually will have a similar question. So what would be the relation between a line in 3D space and a plane in 3D space, right? Imagine that. So here's a question for this one here. For this particular one, how do I know the relationship between the V and the plane and here? Is it parallel, or is it perpendicular? Right. Or is it the next one here? So there's an inclination, right? So let's just call it other here. Okay. So that's what we want to solve for this one. Simple question. Right. And from this stage, everything that you solve is based on dot product or cross product. So it's all about manipulation now between the dot product, cross product. So you only have two choices: dot product, cross product. So always ask yourself, so what should I use, right? Should I use dot product? Should I use cross product? And then what other information do I need in order to solve this one here? Okay. Yeah. You're given a plane and here. So you're given a plane. You're given a vector. And when I derive the plane and here, so I mentioned about what you need, right? What you need to derive plane equation. You need a point on the plane. You need a vector perpendicular plane. Okay. Yeah. And once you have these two information, you plug it into this plane equation. You get a plane equation. Now, but if I ask the other way around, if you're given a plane equation, what are the information that you can immediately derive from the plane equation? If you're given, for example, if you're given a plane equation like this, or if you're given a plane equation like this, what will be the immediate information you can write it down with the given plane equation? Normal vector, exactly, which is basically the coefficient ABC at here, right? So if I given a plane equation at here, the normal vector, let's call it n, is what? 1, 1, 3. Okay, so 1, 1, 3. So that's the sort of a logical reciprocal type of thinking here. If you derive something, what do you need? If you're already given something, what can I write down immediately? Right? That's how you can solve a mathematical problem here, right? You always need to write down the known conditions first. So then you can illustrate, if this is n at here, I'm going to derive. If this is n at here, then this got to be the n vector here, right? It's got to be the n vector. The v here, I'm not sure yet, so I'll just draw the v at here, so we don't know what the relationship. But now we got n, we got the v now, right? So the question can be translated into a slightly different type of calculation now. So if I want to know the relation between v and the plane, I probably can get the same information if I know the relationship between the v and the n at here, right? Okay. So to simply put it, let's calculate the dot product. Yeah, calculate dot product. Because why? Because if the dot product is 0, what does that mean? That means these two vectors must be, if the dot product is 0, the two vectors must be perpendicular. And if the two vectors are perpendicular, and that must be what means the v and the plane must be parallel. Okay, so that's the logic here, right? So let's take a look at the dot product results here. So 1, 1, 3 dot this v, 1, 2, -1. And if you plug it in everything, so 1 plus 2 minus 3 is 0. Okay, so that's good, right? So if 0 means basically you're talking about parallel, a parallel here, right? Yeah. It's very simple, but here's give you, actually in the future, there's so many different type of questions, but all the different questions here requires the fundamental calculations, either dot product or either cross product. But what do you dot, right? What do you cross with? That's the sum of the question. You have to write it down here. Okay? Yeah. So we still have a little bit of time here, so let's take a look at an example. This one here is slightly more difficult. Any questions so far? So good? Okay. All right, so here's a plane given, and a point also given. Okay, so now I'm gonna draw this out. So this is the plane, here's S. And the question here is, find the shortest distance. Find the shortest distance from S to the plane. Okay. That seems like a typical high school type of geometry question, right? So shorter distance basically means you drop the S all the way perpendicular to the plane, and we're looking for this little distance d at here. Okay. Alright, so we may not be able to finish this, but we actually probably will be able to finish this. But anyway, let's take a look at it. So, okay, so how do I approach this kind of question? Right? As I mentioned, it's always about either dot product, either cross product. Okay, but if you cannot think straight at the beginning, right? Your first step to help you is, let's write down all the available information first. Right? All the available information first. So what's available? Of course, the point is available, and the plane is available. And then if you have the plane equation, and that's what I just did in the previous example. If I got the plane equation ready, the immediate information I can write down from the plane equation is, what is it? The normal vector, right? So I'll write down the normal vector here, and I actually will draw the normal vector out just to illustrate. And that's 3, 2, 6. That's our normal vector. Okay. So now we got our normal vector now. So let's think about. You probably don't know. Okay, so I don't think I can write down anything else now, right? So let's just stay as it is. But then let's think about, how do I get the shorter distance now? Okay, shorter distance. So this is also back to basically the few concepts we have just reviewed now, right? Think about basically the few concepts. If I want to get a shorter distance, like here, okay, one of the simplest concept I reviewed at the beginning, when you want to get a distance, you can always what? You can always use a vector, then project that vector to a direction, right? To a direction. And translate it into mathematical language is, you can use the vector, then what? Dot the unit vector. Right. So here is D here. What direction is this D? That direction is this N here, isn't it? Right? That's the direction here. So this is, I'll probably draw this N in here. But this time I'm not going to draw the N anymore. I'm going to draw what? N hat. Is that okay? Right? Draw the N hat. So if I want to use that simple concept, I'll use a vector to dot the N hat, which is going to give me this D. So now the next question is, where's that vector from? Right? Where's the vector from? from what vector to dot this n hat? If you think out loud, I don't give you the vectors in it, right? But can you create that vector yourself? How can you create a vector which dot the n hat give you the d? Yes?
From the point you have on the plane up to your new S.
Excellent, excellent. So you from a point on the plane up to the point S, that's a vector, right? That's a vector. That's an option here. So if you look at this here, you can always form this right triangle here, and let's call it QA here. If you project the QS to the n hat direction, you get the shorter distance d. Okay, yeah, good. And all that, what we did is we just picked a point Q on the plane. How many of this type of point Q on the plane? How many? Infinite. So can you give me a point Q now? Any point Q you want, right? Can you pick a point Q now? How do you pick a point Q on the plane? What would be an option? Yes?
Generate x and y coordinates and just find a z.
Good.
On the plane equation.
Right. But how? But you don't want to complicate the situation, right? What would be the simplest way to generate x, y, z?
Assume they're 0.
Good. Yeah. So can I assume x, y to be 0?
Yeah.
And then what will be the z? 1, right? But you can't assume all to be 0, right? Because if you just put a 0, 0 here, it doesn't satisfy the plane equation. Okay? The bottom line is that Q needs to satisfy the plane equation here. Okay? So now you see, you can literally generate a infinite number of a point Q on the plane here, right? It's up to you. But you can choose the easiest one. So now once I have this now, I'll use the knowledge that I learned from the beginning of the lecture now. So QS equal to 1 minus 0, 1 minus 0, 3 minus 1, and which is 1, 1, 2. Right? That's your QS at here. And then very simply put it, my shorter distance D essentially is the projection of the QS onto the direction n hat, right? Onto direction n hat. And n hat is normalized n vector at here, right? Normalized n vector. So there you go. That's all you need at here. That's all you need. Okay? Now you just have to be careful. You may end up with a negative number. Okay, you may end up with a negative number, but that doesn't mean you're doing anything wrong, because we really don't. Because you see, I illustrate the n hat pointing this direction here, but n hat might be actually pointing to the completely the other direction, right? So that's why you will get a probably negative number here. So typically you can put an absolute sign in here for the calculation. Okay? So I'll leave that calculation to you, and it shouldn't be too bad. Okay? It's a very simple calculation. Right? So you know what? I'll just write it down here. Okay. That's results. All right. Any questions? Okay. Yeah. Thank you. See you Thursday. Remember, the tutorial will start this week. Okay, so I encourage all of you to go to the tutorial.